So the mole is a counting unit that's used extensively in chemistry. And I'm going to go into a little bit more details here in just a second about what exactly is a counting unit, what I mean by that. The abbreviation for the mole is kind of lame. So all you're going to do when you want to abbreviate this counting unit is get rid of the E. It's not shorter, it's not like a lowercase m or anything because that's already played out. We're already using that for milli and meters and mass sometimes. So when we write mole, MOL is the best you can do. Don't abbreviate more than that. Mole Day is celebrated on October 23rd, 1023. So if you really want to geek out, this is the big day for chemists. Just like mathematicians celebrate Pi Day on March 14th. This is Mole Day, and it's part of National Chemistry Week. So the value, where the 1023 is coming from, is Avogadro's number. So Avogadro's number is 6.02 times 10 to the 23rd. This value is usually provided, but you're going to use it so much, it's going to be like first nature. There are more sig figs involved in this number, but typically I just use 6.02. Usually that's sufficient. We can use this with any kind of things, as long as the things are really small and we need to count a bunch of them. So for example, we're going to use Avogadro's number with atoms. Along the same lines, atoms combine, they form compounds or molecules. So we can use it with molecules. Sometimes we need to count ions. I've seen problems where we have to consider a mole of electrons. So you get the picture here. As long as it's really small, we can use Avogadro's number as a counting unit. Let me explain a little bit more about the counting unit. So there's a counting unit that we're all super familiar with. That's a dozen. So you might go, say you want donuts, right? 1 dozen donuts has 12 donuts. So by knowing the definition of my counting unit, I can set up a conversion factor. We can flip this conversion factor, right? We could say 12 donuts in 1 dozen donuts. So what's a counting unit? It's just a defined value that maybe makes our life a little bit easier. So instead of being super specific and sending someone out for 48 donuts, you can say, well, pick up 4 dozen donuts. Same thing with Avogadro's number. And this one's even more useful than a dozen, right? We can say 48, but try saying this number, right? Forget about it. So instead, we call this number of things a mole. Let's do donuts. What if you want a mole of donuts? So we can write a conversion factor that says 1 mole of donuts. And underneath, we would say, well, that has 6.02 times 10 to the 23rd donuts. Super, super ridiculous. I read somewhere that if you had a mole of sand, it would be the size of a mountain. So I don't think we're going to have a mole of donuts anytime soon, but just so we start wrapping our heads around the conversion factor aspect, we can flip this and we could say 6.02 times 10 to the 23rd donuts in 1 mole of donuts. So Avogadro's number is 6.02 times 10 to the 23rd, and 1 mole of anything contains Avogadro's number of things. Using Avogadro's number, I set up two conversion factors. The first one says 1 mole of silver has 6.02 times 10 to the 23rd silver atoms. To get the second conversion factor, I just flipped the first one. I put Avogadro's number on top and 1 mole of silver in the denominator. Now, this is a new area of chemistry for many of you. It's called stoichiometry. However, stoichiometry is just a fancy word for dimensional analysis. And a lot of the technique here should remind you of the approach and the techniques that we used when we were doing our measurement conversions. Just like with our measurement conversion problems, we're going to start with the standalone value. So I'm going to write 2.80 times 10 to the 22nd. Make sure to include units. Units are critical when we're doing stoichiometry. So silver atoms. And I want to get rid of silver atoms. So I'm going to set up a conversion factor with silver atoms in the denominator. And we're looking to go to moles of silver. So that's going to be up top. And then the relationship between moles of silver and silver atoms is Avogadro's number. So 1 mole of silver contains 6.02 times 10 to the 23rd silver atoms. Just like with our dimensional analysis, we can see how things are canceling. So silver atoms will cancel with silver atoms, and we're left with moles of silver. In your calculator, make sure you're using that E key. So 2.80 E22 divided by 6.02 E23. And I got 0.046511628, and that has units of moles of silver. Now, since we only had 3 sig figs with the number they gave us, I'm going to cut this off to 3 sig figs. So I want to report this as 0.0465 moles of silver, or I could use scientific notation. So I could also, depends on what mode you're in, you could also say 4.65 times 10 to the negative 2 moles of silver. Either one of these would be correct. In problem number 10, we need to go from moles to atoms. So I'm going to start with the number, the standalone number. So I'll start with 3.8 moles of sulfur. I want to be as specific as possible. And we're trying to get rid of moles of sulfur. So that's going to go in the denominator of my conversion factor. And I want to go to sulfur atoms. So 1 mole of sulfur has 6.02 times 10 to the 23rd sulfur atoms. So you're going to multiply moles of sulfur, cancel moles of sulfur, leaving us just with sulfur atoms. And I got a value of 2.2876 times 10 to the 24th sulfur atoms. Now, just 2 sig figs with the value that they gave us. So we're going to report this as 2.3 because I need to round up. The 2 is followed by an 8. So 2.3 times 10 to the 24th sulfur atoms. I'm going to start with the standalone number that they gave us, 5.8 times 10 to the 24th aluminum atoms. I need to get rid of aluminum atoms, so I'm going to put that in the denominator of my conversion factor. And the problem asks us to determine the number of moles of aluminum, so that'll go in the numerator. And 1 mole of aluminum contains 6.02 times 10 to the 23rd aluminum atoms. Aluminum atoms will cancel with aluminum atoms, leaving us with moles of aluminum. We want to divide 5.8 times 10 to the 24th divided by 6.02 times 10 to the 23rd. And when I did that, I got 9.634551,495 moles of aluminum. Way too many sig figs in that value. They only gave us 2 to start with. So I'm going to round that to 9.6 moles of aluminum. Starting with the 1.2 moles of carbon, in my conversion factor, moles of carbon will be in the denominator. That way it will cancel out, and I'm going to have atoms of carbon, or carbon atoms. The order there doesn't matter. So Avogadro's number, 6.02 times 10 to the 23rd atoms of carbon in 1 mole of carbon. This cancels, leaving me with atoms of carbon, and I got 7.224 times 10 to the 23rd atoms of carbon, or carbon atoms. But we can only report this value to 2 sig figs because of our starting number. So final answer will be 7.2 times 10 to the 23rd atoms of carbon. Just like we created conversion factors between individual atoms and Avogadro's number, we can do the same with molecules. So here we have a molecule called pentane, and we can say 1 mole of pentane, C5H12, has Avogadro's number of molecules of pentane. And we're counting them as whole units. So each C5H12 counts once. It's kind of like if you have a dozen sandwiches. It has 2 pieces of bread on each sandwich, but you're not worried about the subscript, the 2 pieces of bread. You're just worried about the sandwich as a whole. You're ordering 12 sandwiches. So I put an extra part on this, and hopefully it helps. But on part A, the question is, how many moles of pentane are contained in 5.00 times 10 to the 19th molecules of pentane? So we're going to start with the number that they gave us. So 5.00 times 10 to the 19. And I'm going to write pentane molecules. And I need to get rid of the molecules, so that'll go in the denominator of my conversion factor. So I'll do C5H12 molecules. And then we can go from molecules to moles. So on top, I'll do 1 mole of pentane, C5H12, and then has Avogadro's number of molecules. And just like in previous problems, we see things canceling. Molecules of pentane will cancel molecules of pentane, and we're left with moles of pentane. So I'm going to go ahead and divide 5 times 10 to the 19th by 6.02 times 10 to the 23rd. When I did that, I got 8.3056 47841 times 10 to the negative fifth, and that's going to be moles of C5H12. Once again, way too many sig figs, so let's just cut this down to the 3 sig figs. So I'll do 8.31 times 10 to the negative fifth moles of C5H12. Alrighty, that's for part A, where they asked us to consider the molecule as a whole. A lot of times, you're asked to think about individual atoms within the molecule. So the analogy for this is, I was talking earlier about a dozen sandwiches, and you're like, well, that's 12 sandwiches. But if I asked you about the bread, you'd say, well, I gotta take the 12 sandwiches and multiply by 2, because each unit has 2 slices of bread. Similar idea here. Sometimes I encourage students to think about it. If we were going to build 5 times 10 to the 19th molecules of pentane, how many spheres would we need for those carbon atoms? Start with the number they gave us. We're going to start with 5.00 times 10 to the 19th molecules. And I apologize, I keep on writing it different ways, but the order doesn't matter as long as the details are there. So I'm going to start with molecules of pentane. Still want to get rid of molecules of pentane. And I can't jump, even though in part B we're asked for moles of carbon. I don't have that relationship right off the bat. So I'm going to say, just like I did before, 6.02 times 10 to the 23rd molecules of pentane have 1 mole of pentane, or that's what's in 1 mole of pentane. So this is canceling with this. However, at this point, I need to get rid of the moles of pentane. So I'm going to write 1 mole of pentane on the bottom. What do I know about pentane? Well, from its formula, I know that 1 mole of pentane has 5 moles of carbon. And that's basically another conversion factor that you can get directly from the formula now. And so I'm going to cancel moles of pentane with moles of pentane. And now I'm going to be left with moles of carbon. My answer here had a bunch of digits. 4.15 times 10 to the negative 4. Once I round to the 3 sig figs, and I'm going to say that this is moles of carbon. Take home message here. You can create mole-to-mole conversion factors using the formula for your molecule. Second thing though is you kind of know, if you're thinking about that sandwich analogy, well, we're just multiplying by 5. And you're absolutely right. Just like you'd multiply by 2 if you were considering how much bread is on a certain number of sandwiches. Here we know, since every mole of this molecule has 5 carbons, we can take our previous number and just multiply it by 5 to get the information about moles of carbon. Either way, as long as you're confident about how you're manipulating those numbers and why. So for part A, we're given the fact that we have 5.00 moles of water. we're asked to determine how many molecules of water we're dealing with. So in my conversion factor, I'm going to get rid of moles of water and put molecules of water up top. So there's 6.02 times 10 to the 23rd molecules of water in 1 mole of water. Start canceling stuff. And when I multiply, I got 3.01 times 10 to the 24th molecules of water. Alright, so part B I added on, again, to give us more practice with considering individual atoms within a molecule. So how many hydrogen atoms are in 5 moles of water? There's 2 ways to go about this. You can see that for every molecule of water, if you're going to build that, you're going to have to grab 2 hydrogen atoms. So we can take our previous answer and just multiply by 2. Because if we have 3.01 times 10 to the 24th molecules of water, and then for every 1 molecule of water, as a whole, it breaks down to having 2 hydrogen atoms. And we're going to get 6.02 times 10 to the 24th hydrogen atoms. Of course, we can start with the 5.00 moles of water. Our conversion factor will have moles of water on the bottom, and then molecules of water in the numerator. It's really important to note here that when you're using Avogadro's number, you can't mix and match. So 1 mole of water has Avogadro's number of water molecules. And we can't just skip to hydrogen atoms. They have to correspond, the thing in the numerator and the thing in the denominator, when it's Avogadro's number. So moles of water cancel. Now we need to get rid of molecules of water. So say 1 molecule of water contains 2 hydrogen atoms. And now molecules of water will cancel with molecules of water, and we're just left with hydrogen atoms. So our answer will be the same, 6.02 times 10 to the 24th hydrogen atoms.